Okay, we're continuing on with equilibrium, and we're going to talk about something called the reaction quotient. Reaction quotient is calculated the same way as the equilibrium constant. So if we have a reaction, generic reaction, little a plus little b of little b, in equilibrium with little c of little c and little d of little d, or I should say equilibrium, going back and forth. If we take it any time, and same way with the concentrations or the pressures for QPs, we get the reaction quotient. And the Q, reaction quotient, is any given time. The equilibrium, the quotient, and the equilibrium constant are the same thing. If we only have reactants, that means we have zero products over some number. That means that the reaction quotient is zero. If there's only products, that means we get some number over zero. Then that's equilibrium. That's a singularity. So, okay, and at equilibrium, the quotient is equal to the equilibrium constant. I've already mentioned that. If Q is smaller than K, so I was thinking about this, is if Q is less than K, that means that we have too little products and the top number is too small and the bottom number is too big, so that means that more products will form and more reactants will be consumed, so it shifts right towards the products. If Q is too big, that means that we have the top number is too big and the bottom number is too small, so that means the equation will shift. Products will be consumed and then more reactants will form. It'll go towards the reactant. It'll shift left. And I tend to think of it that way. If a graphical method, there's a graphical method Q or K. So alongside on the left on the y-axis, on the x-axis concentration. So if the Q is greater than K, that top number is too big, so it's going to shoot left. If Q is smaller than K, the top number is too small, so it's going to grow bigger. It's going to shift towards the products. Okay? So if that makes more sense to you. I like the math argument better myself. Consider the following reaction is equilibrium constants. And the K, so I2 plus Cl2 makes 2 ICl. The Kp is 81.9. Reaction mixture has 0.114 atmospheres of iodine, 0.102 atmospheres of chlorine, and 0.355 atmospheres of ICl. So let's put in the numbers. So we have 0.3, actually make my pen bigger, 0.3, let's erase this, 0.355 squared for 0.14 times 0.102. And I'll go ahead and put this in my calculator. It's pretty straightforward. 0.355 squared divided by 0.114 divided by 0.102. And I'm getting 10.8. 10.8. So 10.8, that means that it's less than K, but I always think of it logically. So if it's too small, that means the top number is too small and the bottom number is too big. So that means we're going to shift right. So this means it's a shift right towards the products so that more products can form, make that bottom number bigger and the denominator smaller. Okay. And what we're doing here is I'm trying to build up your arsenal of different types of problems so you get used to looking at these problems, and it is up to you to take these problems and attack them. So look at this problem. So COF2 fluorophosgene, I guess, fluorophosgene in equilibrium with carbon dioxide and carbon tetrafluoride. Kc is 2. And an equilibrium mixture concentration of COF2 is 0.255 mole and the concentration of CF4 is 0.118 molar. What is the equilibrium concentration of CO2? So when you look at this problem, you have to look at what the given information is and where you need to go. So we're looking for the equilibrium. This is what we want. We want the equilibrium concentration of CO2. And we're given a Kc, and we're given everything but 1. So let's write out the Kc. Our Kc is going to be products, CO2, carbon tetrafluoride, all over COF2 squared. This equals 2. And then we don't know the CO2. I'm going to call that my x variable. We know that carbon tetrafluoride is 0.118, and we also know the fluoroform, or whatever, not fluoroform, fluorophosgene is 0.255 squared. So what we can solve for our unknown, and this is the concentration of CO2, and it's going to be 2 times 0.255 squared over 0.118, and you have to look at this and you have to figure out what the given information is. Like I said, the given information and what you can figure out. You're not told explicitly what the equilibrium constant expression is. Ooh, sorry, let me pause it. I dropped my iPad. Okay, I've retrieved my iPad and I went ahead and threw it in my calculator, so didn't damage the iPad, don't worry. But I was talking about the given information, so you weren't explicitly given the equilibrium, the KEQ formula. That's something you have to figure out on your own. So this is something you have to look at this information, you have to look at what's given, and you have to come up with a plan. And so you have to think, okay, I need to have an equation that equates as I only have one unknown, so I just need one equation. The number of equations independently relationships are the number of unknowns. That's called a degree of freedom. So you have one degree of freedom. So you have to find a way to have a equation that includes the equilibrium concentration of CO2 that would include some other relationship. And the equilibrium expression is one of these. Well, it would be the only way for this one. And I'm hoping by watching me do some of these, you start to learn how to attack these problems. Okay, and I mentioned before that these ice charts will be important. And so if you don't recall, look at the previous video for this chapter. But let's look at this reaction. Nitrogen plus oxygen makes 2 nitrogen monoxides. Kc is 0.1 at 2,000 degrees Celsius. Initial concentration of N2 and O2 are 0.2 molar. What is the equilibrium concentration of reactants and the products at this temperature? So I have written out the chemical equation, and I see I means initial, C means change, E means equilibrium. Initially, we have 0.2 molar of both of this, and since it's not included, I'm going to say 0 for that. So let's talk about the change. So we have reactants only and no products. So because of this, we're going to shift right towards the products, and we're going to lose one extent of reaction of nitrogen, one extent of reaction of hydrogen, and we're going to gain 2 extents of reaction of nitrogen monoxide. So just so you know, if you want, you can equally call this x, and you can call these x divided by 2's. If you want to do this, is a perfect valid way to do it. I don't like to do it this way, but remember, when you choose your variable, stick with it, because if you change it in the middle of the setup, you're going to get the wrong answer. So I'm choosing the extended reaction to be the destruction of nitrogen and oxygen, and this means the equilibrium. I'll go back to blue. So equilibrium is going to be 0.2 minus x, 0.2 minus x, and then, oh wait, I'm sorry, this is plus 2x. This is going to be 2x. So now we do our expressions. So our Kc is 0.1 is going to be equal to concentration of NO squared all over the concentration of N2O2. So 0.1 equals 2x squared all over 0.2 minus x, 0.2 minus x. So which equals 2x squared over 0.2 minus x squared. So what's nice about this is we can take the square root of it, right? So we can take the square root of both sides. Square root of 0.1 is 2x over 0.2 minus x. And now we just solve for x. So multiply both sides by 0.2 minus x, square root of 0.1 times quantity 0.2 minus x equals 2x. Now we FOIL this. So 2 square root of 0.1 minus x square root of 0.1 equals 2x. And then we add x to both sides, get the x all on one side. 2 square root of 0.1 equals 2x plus x squared of 0.1. And we can bring out the x. 2 plus the square root of 0.1. And now we can divide both sides by that. So 2 square root of 0.1 all over 2 plus the square root of 0.1 equals x. And then we put this in our calculator. So we put that in the calculator, and I forgot to put the 0.2 there. We solve x is 0.027. So then we go back up here, and we apply x equals 0.027. So that means that NO, it's 2x. That's going to be 0.054 molar, and each N2 and O2, so this is going to be 0.173 molar. And I'm just applying the 0.2 minus x and the x value being there. Okay, so something though you might notice, so when you take the square root of both sides here, so when you take the square root here, you should get plus and minus square root of 0.1. And I chose to keep the positive 0.1. I didn't even talk about the negative. So this is a problem in mathematics. So the fundamental theorem of algebra, x to the n has n roots. You raise something to the n power, there's going to be n number of roots. And mathematically it would be possible, but physically it wouldn't make any sense. So mathematics is a very, very powerful model, but math is not real. Math is not real, it's a model, and it's only when humans apply the model to something that's worthwhile I guess it's not necessarily humans, it's just the way nature works, but we as humans are using math as a tool, and we have to determine which answers are real, which ones are false. So whenever, if you raise something to the third power, you're going to have 3 possible answers. You can have, and they could be repeats. You can have multiple roots, but frequently you get one or more that doesn't make any sense, and then you have to determine which one makes sense and which one doesn't. It's pretty simple, straightforward for this one, but the next problem, it's going to be a little more difficult to figure out which one is real and which one's not real. And what happens is something happens that's physically impossible. And again, this is mathematics. Mathematics is a model, and it's a very good model, but it can cause some issues. So here is the next one that's a little more difficult. consider this reaction, N2O4 in equilibrium with two NO2s, and Kc is 0.36. Initially, the concentration of NO2 is 0.1 molar. What is the equilibrium concentrations of NO2 and N2O4? So we have N2O4 in equilibrium with two NO2s. And then I normally don't even write concentration. I'll go ahead and put it in there anyways. So initial change, equilibrium. So initially, we have this be 0.1 molar. So that means initially this is 0. So where are we going to change? We're going to gain x of this, and we're going to lose 2x of this. Why are we losing 2x? Because of the 2 there. Okay, in equilibrium, this is going to be x, and this is going to be 0.1 minus 2x. So let's look at the equilibrium constant. The k is going to be product NO2 squared all over N2O4 to the first power. And this is 0.36. And this equals 0.1 minus 2x squared all over x. And now drat. We have a quadratic equation we have to solve. So solving for x, the extent of reaction here, we're going to have to solve it. All right, so let's go ahead and solve it. So 0.36 times x equals 0.1 minus 2x quantity squared. Now here's a math trick. There's something called Pascal's triangle. So this is Pascal's triangle. And with the second line here, you can use that relationship to FOIL this one squared. So it's the first one squared. This is 0.01 plus 2 times the sum of that. So 2 times the multiplication of these two. So it's going to be 0.4x, right? Because 0.1 times 2 is 0.2, and 2 times that is 0.4, and plus 4x squared. So what we need to do to solve the quadratic equation, we need to get it in this form though. So let me go ahead and set that equal to 0. So we have 4x squared, and we're looking at these lines here. We're going to set it to 0. 4x squared, we subtract 0.36x from both sides, minus, actually no, it's plus 0.04x plus 0.01 equals 0. So now we have to apply the quadratic equation. And I just realized I made a mistake. This here is minus. I forgot the minus sign in there. So this is gonna, I thought I was doing something wrong. So this is gonna be minus 0.76x. So then we apply the quadratic equation. So it is negative, x equals negative b, so x equals negative b, that's positive 0.76 plus or minus the square root of b squared, 0.76, well, it's minus, squared minus 4 times a, which is 4 times c, which is 0.01, all over 4 times 2. And I'm going to cheat and look in the textbook, and x equals X is going to be equal to 0.176 or 0.014. Now, we have to decide which one of these makes sense. And if you look at this, if the initial concentration of nitrogen monoxide is 0.1, if we do 0.176, that's going to give us a really negative concentration. Because of that, we have to discount this value. And it's because of the fundamental theorem of algebra. Okay, so that's all it is. It's just the fundamental theorem of algebra. So fundamental theorem of algebra gets rid of that, and the fundamental theorem of algebra is the reason why I get two answers, but we have to apply it. So now find the equilibrium concentrations of that. So let's put our x equals, what is our x equal? 0.14. 0.014. That means that the N2O4, this is going to be 0.014 molar, and 0.1 minus 2x, so this is 0.1 minus 0.028, and that is going to be 0.072 molar. So there we have it, equilibrium concentrations of those two using this. So let me recap this one. This one's a long one. Okay, so we have this equation here, N2O4 in equilibrium with two NOs. Initial conditions is 0.1 molar for nitrogen monoxide, and we're given the Kc is 3.6. By using our ice chart, initial change equilibrium, well, since we were given initial conditions for the product, we assume it's 0 for the reactant. We shift left back towards the reactants, and we're going to gain one extent of reaction of N2O4, and we're going to lose two extensive reaction of NO2s. And then the equilibrium value then is x for N2O4, and it's 0.1 minus 2x for NO. And then we set our equilibrium expression, so 0.36 is 0.1 minus 2x quantity squared all over x. And we FOIL this, and we have 4x squared minus 0.76x plus 0.01 equals 0. Apply the quadratic equation, we get x equals 0.176 and 0.014. 0.014 is the only answer that makes sense, so we plug that back in, and we get 0.014 molar for the N2O4 and 0.072 molar for nitrogen monoxide. So, if you want, you can check. So there's a check here. You can go ahead so if the equilibrium expression is in fact NO, that we can take we can see if 0.36 does it equal 0.072 squared all over 0.014, and if we do that, I'm going to look in the book, we do that and we find it's 0.037, which is pretty close to 0.36. So that's one way. I mean, if it's way off, then you know you screwed something up. But this one, actually, you can check it to make sure it's okay. All right. Next example. Oh, I hate you in the quadratic equation. Anyways, next one here. So two hydrogen sulfides in equilibrium with two hydrogens plus SO2. So a half-liter reaction vessel initially contains 0.0125 molar of hydrogen sulfide. What is the equilibrium concentration of the products hydrogen and sulfur, diatomic sulfur? This just means the concentration is 0.025 molar. So let's go ahead and do this. And initial change equilibrium, the initial condition 0.025 molar. This is 0, this is 0. So the change, we are losing 2x, we are gaining 2x of this, and we are gaining x of this. Equilibrium 0.025 minus 2x, 2x, and x. So our Kc is equal to H2 squared S2 all over H2S squared. And this is 1.67 times 10 to the minus 7 equals 2x squared times x all over 0.025 minus 2x. Okay, so there's a trick here. This looks horrible, doesn't it? Now we have a cubic. Oh, so it's going to be 4x cubed on top. This is going to be horrible, but we can do an approximation. So we can ignore this 2x here. So you can. So the idea with this is that Kc, so 1.67 times 10 to the minus 7. That's a really small number. That means this reaction is not going very far. Okay, so this is a very, very small reaction. And because of that, 0.025 minus 2x, what we can say is that this is approximately going to be 4x cubed all over 0.025. So we can discount this x. And in the discounting of the x, this will work only if we relate it to something that's much, much bigger. Does that mean that the x is on top? Can we say, like, well, you know what, this number is approximately 0.4x cubed. Let's discount the x and the x cubed. And that's true that 1.67 is approximately 0, but it doesn't tell us any useful information. So when can we discount x? When can you not discount x? It depends on how well you need to know the information. In lots and lots of equations in engineering and in science in general, E equals mc squared ignores a bunch of terms to get that. There's more terms in E equals mc squared than just those four. That's you assume certain terms are negligible. Happens all the time. This might be the first time you see it, but you'll see it frequently in more advanced classes in science and engineering. It has to do with the relation of that to this other number, this 0.025. It also depends on how accurately you need to know the information. So, like the Deep Impact Probe, when there was a projectile that was shot from a satellite that hit a comet. I mean, can you imagine the trajectory calculations to get that right? All the gravity and I mean, you have to include the gravity of the moon, gravity of the Earth, gravity of Jupiter, and that kind of thing. That must have been a horrible, horrible calculation. If something like that, you have to make sure you don't neglect something this big. But for an application like this with a few sig figs, this one is acceptable. Okay, so this is an acceptable, acceptable, say, discounting. So what we're at right now, 1.67 times 10 to the minus 7 equals 4x cubed over 0.025. Okay, so then we have, let's put all the numbers on one side, 0.025 times 1.67 times 10 to the minus 7 over 4 equals x cubed. So I can take the cube root of this and get rid of that, and then put this in the calculator. I will put it in the calculator. Okay, here is the answer in the calculator, and if you want to know how to do the cube root, you can raise it to the 1/3 power. And in putting the numbers, I realized I forgot to put the squared on the H2S, so I fixed that there. Okay, so hopefully you can see that some of these get easier now that you can start to discount some of the variables. So why don't you try that? Oh, let me recap this one. You probably want to recap for this one. So let's look at this case here. So we have two hydrogen sulfides in equilibrium with hydrogen and sulfur. Initial change equilibrium, we have 0.025 initially of hydrogen sulfide, 0 of the products. So we lose two extensive reaction of the reactants. We gain 2 extents of the reaction for hydrogen, 1 of the sulfur, diatomic sulfur. Equilibrium is 0.025 minus 2x, 2x and x for hydrogen and sulfur respectively. Equilibrium constant is products, so hydrogen squared over sulfur over H2S squared. We're given the equilibrium constant is 1.67 times 10 to the minus 7. And then we have 2x squared times x over 0.025 minus 2x quantity squared. And we can discount that 2x because of the very small extent of reaction that we're going to get because the equilibrium constant is small. And then we make that assumption, and then we solve for it. We get x equals 2.97 times 10 to the minus 4. So, and if you look at that, so that's 0.0003. So that's really small. That's pretty small compared to that. It's more than 100 times bigger. It's about 100 times bigger, the 0.025. So it's dropping by about 1%. So there is a little bit of error associated with this. Now, if you have a sweet calculator that has a solver function, go ahead and use it. If you want to use your solver function, your calculator, then go right ahead, and then don't worry about discounting the x. But if you don't have a sweet solving function, then discount the x. So, but anyways, we solve for x, and I guess we have to do the equilibrium concentration. I didn't do this part. So equilibrium concentration of this, hydrogen and sulfur, so it's just going to be, x is that. This is going to be 5.94 times 10 to the minus 4, and 2.97 times 10 to the minus 4 for that. So there is our answer. So finding equilibrium concentrations of H2 and sulfur is just taking the x and plugging it into the equation like that. Okay, so why don't you try this one? And the hint is you can discount x. So why don't you give it a try? Okay, so if you've worked on your own, hopefully you get something like this, where the answer is going to be 2.28 times 10 to the minus 4 for the extended reaction, and that's going to be chlorine exactly. Okay, so next one is Le Chatelier's principle. And this Le Chatelier's principle said equilibrium will shift to counteract a change. So this is true for just about anything. So this is not just chemistry. This is for all equilibrium. So if you were to come up and push me, so if I were to be pushed this way, I have to push in the opposite way to stay in equilibrium and not fall over. So that's a simple one. Let's look at a different example. Let's say you win the lottery. I know that we don't have lottery here in Hawaii, but let's say you're traveling to California and you win the Powerball. Suddenly you have $200 million. And what are you going to do? Is it you're like, well, you know what? I think it's time that I start eating more crock-pot meals. I'm going to stay in and watch Netflix. No, you're probably going to start throwing wild, crazy parties, right? So if you've got all this money coming in, you're going to get it out. You're going to find some way to spend it. Same thing if you lose your job, suddenly you have a great job, lots of income, and you lose your job, you're like, well, time to go buy a new car and go on a trip. Like, nope. If you suddenly have a great decrease in your income, you're going to try and conserve your wealth, at least until income increases, right? So that's the essence of Le Chatelier's principle. The equilibrium shifts to counteract a change. So look here in this general equation here, we have reactants and products. Reactants on the left, products on the right. So if the reactants increase, what happens is the system will shift right to get rid of those reactants. So too many reactants, we will shift right and get rid of them. Likewise, if the reactants go down, it shifts left. So we're losing reactants, well, better make more of them. The reaction will shift left. If the products increase, then the system's going to want to decrease the products. It'll shift left to form more reactants. If the products disappear, well, it's going to shift right to form more of them. So a catalyst for equilibrium, this causes no change in the equilibrium. Catalyst will do nothing for the Le Chatelier's principle. It just means it'll get to equilibrium faster. So if you add heat, so an exothermic reaction, heat is a product, it will shift the reaction left. If it's endothermic, heat is a reactant, it will shift the reaction right. If you take heat away, for an exothermic reaction, we're going to shift right. We're going to try and heat up. If you take heat away for an endothermic reaction, it's going to shift left. And this doesn't come into play of the fact that chemical reactions, they'll slow down if you take away heat, of course, and they speed up if heat is added. But this is just how the equilibrium will shift. What about for moles of gas? So if say we have a reaction here where there's more moles of gas on the reactant side than the product side, so ammonia synthesis, so 4 moles of gas on the left, 2 moles of gas on the right. So I think in terms of pressure. If you increase the pressure, the system is going to want to shrink down. How does it shrink down? It goes to the side of the lowest moles of gas, shift right. If the pressure decreases, the reaction is going to kind of spill out, like I'm going to pick up more space. It's going to shift left. And then the volume works the same way as pressure, except it's inverse. Increasing the volume is the same thing as decreasing the pressure. You're going to shift left. And decreasing the volume is the same thing as increasing the pressure by Boyle's law. Now, this is opposite. If you have like a reaction here, SO2, Cl2 in equilibrium with SO2 plus Cl2, all gases, so more moles of gas on the right than the left, it's opposite, exact opposite what I said. Increasing the pressure will cause a shift left toward the lower moles of gas. And decreasing the pressure will shift right to the more moles of gas. So you have to look at the equation and sort it out. So let's look at this chemical reaction. All gases, 2 hydrogens plus 2 oxygens makes 2 H2Os, and it's exothermic. What happens if we add hydrogen? Adding hydrogen is a reactant. We will shift right towards the products. What happens if we take away H2O product? We will shift right to the product. What happens if we take away heat, energy, temperature? We will shift right towards the product because heat is a product. What if we add a catalyst? The catalyst causes no change. It just makes things go faster. What happens if the pressure goes down? If the pressure goes down, we shift to the side that has the higher moles of gas. It's shift left. So this is something that's very important, Le Chatelier's principle. It's very easy, and it is very important because it can tell you a lot of information about something very quickly. And many people don't know it, so it can make you look very intelligent. So remember that in your future non-chemistry classes. Chemists tend to know this stuff, but non-chemists tend to have a hard time with it. So think about this next time you are in a economics class or a biology class, and what's going to happen to this system? You can use Le Chatelier's principle, and you can figure things out that way. Like I said, it applies in not just chemistry, it applies to economic theory as well. So, well, that's it for this chapter. I will see you for the next chapter.